Hello, for today's video lecture we're going to be talking about two-dimensional kinematics, specifically in the rectangular coordinate system. So with this, we're talking about curvilinear motion. So curvilinear motion is any motion that follows a curved path. And if it's following a curved path rather than a straight line, we cannot approximate this as a one-dimensional problem anymore. So as a subset, in this course we're going to be talking specifically about planar motion, which is any curvilinear motion that's going to follow a curve in a single plane. So we don't have to worry about full 3D problems just yet. So with that single dimension, we only had one variable, we had one number for position, but to describe a position in a two-dimensional problem, we need at least two dimensions. We're going to need to have the x and y coordinates for rectangular, or like a direction and a distance for polar coordinates, etc. Somehow we need two of these dimensions to describe any position. So options for how we deal with these problems are going to be the following. So we can have the rectangular coordinate system or Cartesian coordinate system. This is where we measure horizontal position and vertical position from some stationary origin point. So the origin point is stationary and the directions x and y, usually for a rectangular, are going to remain constant. We could also have a normal and tangential coordinate system. These are coordinates that are attached to the object in motion. So you can imagine if you're riding in a car and you kind of define all the positions with respect to your kind of moving origin point, yourself inside the moving car, that would be normal and tangential coordinates. And the last one is polar coordinates, where we have a fixed point on the map that we're measuring everything from, but our coordinate system rotates to track the object that we're looking at. So looking at rectangular coordinate systems, this is what it's going to look like. We're going to have an x and a y direction. We're going to have some fixed point O, and we're going to have some particle that we are tracking P. So we represent the position over time, or the position in general, with the r vector. So the r vector is the vector going from the origin point to point T. And as the object moves, that r vector is going to change. Now to define the r vector, we break that r vector down into x and y components. The x component might be changing over time, the y component might be changing over time, and we multiply x component by the I unit vector, which is the unit vector in the x direction, and the y component for position times the j unit vector, which is the unit vector in the y direction. So this is our starting point for analysis. And to really utilize rectangular coordinates, we should have independent motion. That's when it works best. We can always use it in any case, but it might get really complicated in some cases. So what do I mean by independent motion? This means that the direction of the forces, and thus the direction of the accelerations, do not depend upon the position or orientation of the body. So an example of this is projectile motion. This is where most of our rectangular coordinate system problems are going to lie. With this, as a body moves through the air, it's following a curved path, but the gravity force is going to be the same no matter where the object is. So the gravity force is always pointing down, and it's going to have a uniform direction throughout the whole process of the basketball moving through the air. Contrast this with something like a tetherball. So we still have gravity force, that's got a uniform direction, that's all well and good, but the tension in that wire is going to be different depending on where my body is. So as the thing moves around the pole, the direction of the rope changes, the direction of the tension force is going to change, and that's going to make analyzing this problem with a normal tangential coordinate system, or sorry, with a rectangular coordinate system it's going to make it really difficult to do in this case. All right, so assuming we do have independent x and y, if we do have independent directions, we can simply break the x and y pieces to this down into an x part to the equation and a y part to the equation. So I would have x of t, the x position over time is equal to something, take the derivative of that to find the velocity over time in the x direction, and take the derivative of that again to find the acceleration in the x direction. So this is like a one-dimensional problem at this point. And we can do the same thing with the y direction. independently. So I'm going to have a y position equation, a y velocity equation, and a y acceleration equation in all of this. So what links everything together is t. At any one time, it's still a single point. I've got an x and a y coordinate, but that x and y coordinate is a single point in space. At any one time, I've got a x and y velocity, and that's going to be, I can add that together into a velocity vector that has a magnitude and direction, and same thing with acceleration in all of this. So we can take all of this. The position vector has the x and y component, the velocity vector has the x and y component, and the acceleration vector has the x and y component. And this is similar to what we just did with the forces, like in statics. So say I've got x dot and y dot, and my x and y velocities. Say I wanted to know the overall velocity vector. How would I find the magnitude? How would I find the direction? So to find the overall magnitude, we simply use the Pythagorean Theorem. We have right triangles, a squared plus b squared equals c squared. Or in this case, the overall magnitude of the velocity is going to be the x velocity squared plus the y velocity squared at any one given time. Take the square root of that, find the magnitude of my velocity, and the magnitude of your velocity is also your speed. To find the direction of travel, or the trajectory of the body at any one time, I would use the inverse tangent function. So in this case, the y velocity divided by the x velocity, inverse tangent of that would give me theta, where theta in this case is the angle from the trajectory down from the x-axis in this case. So with that, that's all I have for today's lecture. Thank you for watching and hope to see you again.